Howdy. I'd like to talk to you for just a few minutes about the use of horizontal representative rectangles in computing areas. And the reason that this comes up is that sometimes our regions are given to us in terms of functions of y. So for example, consider this. Consider R defined by f of y is equal to y squared plus 1, and g of y is equal to 0, and the lines y equals -1 and y equals 2. What does this mean that we have functions of y? Well, what this means is that we are giving x coordinates in terms of y. And when we graph our x coordinates in terms of y, we're now going to end up with functions of y that are our x coordinates. So for example, the curve x equals y squared plus 1 is going to be a parabola, but it's going to be a parabola on its side. And you can check by plugging in some points. Y equals 0, y equals 1, y equals -1, and so on and so forth, that this parabola is in fact the right shape. Let me erase those points so that we can have a little bit of room to work here. Likewise, the curve g of y equals 0 means that our x-coordinate, no matter what y I plug in, our x-coordinate is going to be 0. So this is g of y equals 0. And the curves, the lines y equals -1 and y equals 2 are exactly what you think they are. They are horizontal lines. And now we have the region, which is this region right here. And what we'd like to do is to find the area of R. It should be clear that if I try to do vertical representative rectangles, then I run into some problems. And the first problem that I run into, well, here's one representative rectangle, and that's fine. But here's another one, and it's kind of awful because the middle part of it's hollowed out. So I'd really have to like split up my rectangle into 2 portions or something terrible like that, and I'd rather not. So instead of doing vertical representative rectangles, I'm going to use instead a horizontal representative rectangle that goes across. And what inspires me to do that is that when I draw my horizontal representative rectangle, it has a height of dy, and it has a width that is defined by this x-coordinate minus that x-coordinate right there, and both of those x-coordinates are given to me as functions of y. So I can immediately write the area of my representative rectangle as the width of this rectangle, which is the distance from here to here, which is the right curve minus the left curve, times the height of my representative rectangle, which is dy. And the area is now going to be the sum from the very lowest representative rectangle up to the very top one, all the way from y equals -1 to y equals 2, of right curve minus left curve. The left curve is invisible because it is x equals 0, dy. And this integration is now delightfully simple. Giving us 8/3 plus 2 minus -1/3 minus 1. And that's going to give us, let's see here, 9/3 plus 2 plus 1, which is 6 as an area. So the basic technique for horizontal rectangles then is sketch as we had before. Draw a horizontal representative rectangle whose height is going to be dy and whose width is going to be right curve minus left curve. And so then the dA, the little element of area that we're adding up, is going to be f minus g dy, so that the total area is now the integral from, and here I'm going to use c and d as my limits of integration to emphasize that the limits of integration here are y values and not x values. They are the very lowest y all the way up to the very highest y. And there it is. Now you may ask, how did I know to do horizontal instead of vertical rectangles? And the answer is that horizontal rectangles are now a tool in your toolbox which you may pull out when it is convenient. Well, when is it convenient? The reason that horizontal rectangles were convenient here was twofold. First of all, I had my x-coordinates given as functions of y. And that meant that I could immediately express my integral in terms of y without having to do any algebra work. So when you have your x-coordinates given to you as functions of y, that suggests that horizontal rectangles might be a very good idea. And the second reason is that when I tried to create vertical rectangles over here, I found that some of my vertical rectangles had real problems. In particular, they had missing area, missing space in between. And that suggested that vertical rectangles was going to be really inconvenient. I would have to do some kind of splitting up of my region into top and bottom parts. Whereas, when I drew representative rectangles that were horizontal, I could see that all of them were nice and solid all the way down. Sometimes we may have an ambiguous situation. And if we have an ambiguous situation, the good news is you may choose either vertical or horizontal rectangles to work with. I want to consider this scenario. Let's say we have a region R that is defined by y equals 2 root x and x equals y over 2, and we now want to find the area of R. So we begin by sketching. Of course, y equals 2 root x is not too hard to sketch. And x equals y over 2 is a very thinly disguised version of y equals 2x. Or a straight line that comes up like so. We need to find the intersection points. So we set y equal to y, 2 root x equals 2x, or root x is equal to x, or x equals x squared, which has the solutions x equals 0 and x equals 1. So we have the intersection points 0, 0 and 1, 2. Now, do I do horizontal or vertical? Well, it turns out I could do either one. If I do the vertical rectangles, which is what you're used to, then I'm going to label those rectangles with a width of dx, and the height of the rectangles will be top curve minus bottom curve. So that with vertical rectangles, dA is equal to top curve, or 2 root x, minus bottom curve, or 2x, and all of that times dx. And the area is now going to be the integral from the first x to the last x. from 0 to 1 of top curve minus bottom curve dx. And now we have a fairly easy integration. Let's pull the constant 2 to the outside. Well, we'll do it like this. Add 1 to the power, divide by the new power, giving me 2/3 x to the 3/2 minus 2x squared over 2 from 0 to 1. And that's equal to 4/3 minus 1, which is a total area of 1/3. But let's suppose that instead I had decided to use horizontal rectangles. Well, in that case, I would label my horizontal rectangle with a height of dy so that my dA is now going to be the right curve, which is x equals y over 2, minus the left curve. Now the left curve so far is expressed as y equals 2 root x. But I need to express it in terms of y, and the reason I know that is that my height of my representative rectangle is dy, and that forces me to express everything in terms of y. So if I come back to the equation for this curve, I can now solve for x in terms of y with a little bit of simple algebra. X is equal to y squared over 4. And that is the equation for my left curve in terms of y. So dA is equal to y over 2 minus y squared over 4. And the area is now going to be the integral from the first y, which is 0, all the way up to the last y, which is 2. Just like so. And now we can go through and integrate and get y squared over 4 minus y cubed over 12 from 0 to 2, which is equal to 4 over 4 minus 8 over 12, or 1 minus 2/3, which again is 1/3. What's remarkable is that these two integrals, here and here, look so very different from one another, and yet they give us the exact same value. It is remarkable, although it's a little less surprising when you recognize that really what we're doing is substituting in each integral. What's the moral of this story? The moral of this story is that in this particular situation, we could use either vertical or horizontal rectangles, and both were just about equally easy. There will be some circumstances where vertical is better. There will be some circumstances where horizontal is better. And sometimes the only way to determine that is to try each one and see which one works out. If you find one that works, go with it. But if you are stuck trying vertical, let's say, then see if a shift to horizontal rectangles might not make your life easier. I hope this was helpful to you, and I'll see you